Okay. We've got F and we've got I. What else? That's it? Nobody else? Harwin's got another one? M. Okay, let's do M. We have not already signed up for H, but F and H are basically the same thing.
Yeah.
But we'll do H because it's an interesting one. K. You want K as well?
Yeah.
Okay. Okay, so I've got F, H, I, K, and M. Anybody else going once? Akam? T, the very last one. Okay, anybody else going once? Twice. 3 times. Go faster, Kyla. Learn faster. P. Okay, here we go. So these are the ones that you wanted me to go over. I will look at them in a little bit more detail here. We're going to go in alphabetical order. So F. Now, I've given you techniques for finding greatest common factor, but you don't have to use a tree every time if you can start to see these things clearly without having to break it down that way. So, for example, I've got negative 4ab and I've got 10b. Looking at the coefficients, yes, Harwin? I can pull a b out from both, absolutely. What else can I pull out from both? Is there anything I can divide out of 4 and 10? 4 and 10 are both even, so I can divide out a 2. And that first term is negative, so I want to factor that negative out as well as part of my greatest common factor. So what I'm hoping we're able to identify is that the greatest common factor of negative 4ab and positive 10b is negative 2b. That's the GCF. And then what we're going to do is we're going to divide each term by our GCF, and then whatever is left is going to go in that set of brackets. So negative 4 divided by negative 2 is? There's nothing to divide the A, and then B divided by B cancels. Bam, it's 1. And then 10 divided by negative 2 is? Negative 5. And then B divided by B cancels. So there we go. My factored form is negative 2b bracket 2a minus 5. Okay, so let's look at H. H is not a difficult one, but H, I actually saw a few of you do an alternative way, and you got a different answer for it, which is interesting. So one of the things I saw from H, if we want to recall, the answer I gave you was negative 12 a minus b. Are we cool with how I got there? Okay. Anybody unsure about how I did that? You did it the other way. Yeah. Well, the biggest number that comes out from 12 and 12 is 12, and I want my leading coefficient to be positive, so I'm going to divide out the negative here. So I want the leading, I want the A, I want my first term to be positive. I want my first term to be positive, so I'd factor out the negative with my GCF. That's going to give me negative 12 a minus b. But at least one of your classmates decided to say, you know what, if I don't want the leading one to be positive and the degree here is the same, is there any reason I couldn't just do this first? Because negative 12a plus 12b is the same thing as 12b minus 12a. Do we see how that's the same thing? So then this individual said, okay, well, what's the GCF of 12 and 12? It's going to be 12. So that's going to be 12 b minus a. Do we see how those two things are exactly the same? if I went back to this first one here and I multiplied that negative back in, I would get negative a plus b, which I could then just rewrite as positive b minus a. That is this negative distributed back in here. This is exactly the same, and I'm glad this particular individual, I'm actually really glad asked the question, because this is a technique that's going to show up in a whole bunch of different ways. Recognizing that by pulling out a negative, I can rewrite and reorder what's going on inside the brackets is going to make your life really quite nice with some of the stuff that's coming up here. Okay? And then there was I. The GCF, I don't know what was our question with I. What's wrong with I?
I got 6 to negative 6.
Well, you want the leading coefficient to be positive.
I got 6 bracket negative x minus y plus z.
Yeah, but you want that leading coefficient to be positive.
Oh, okay.
So you just pull out the negative with the 6, factor out negative 6, and it becomes x plus y minus z.
Okay, so there we go.
Yeah. Harwin, your hand went up and down a couple times, and now you look perplexed. What's you have a question?
I got negative bracket x equals y. Yeah.
No, that is not.
What?
So let's take a look again. You got to be real deliberate when you're doing the division here. If it helps, once you've determined what your GCF is, divide each term by it. Negative 6 divided by negative 6 is? No, it's not 0. It's positive 1x, which we can just write as x. Anything divided by itself is 1. The negative 6 divided by negative 6 is going to be positive 1, and the y is going to be there, so it's going to be plus y. And then positive 6 divided by negative 6 is negative 1, which is going to become negative z when I multiply that z in there. You've got to be really deliberate about what it means to factor out these GCFs. Sorry? Got what? But I want my leading term. I want my leading term to be positive, so I'm going to factor out the negative with it, and it just flips the signs. I don't know if I understand what you mean. You don't understand what you mean? Okay. Then let's carry on, and perhaps we'll drag you kicking and screaming into understanding. Yeah. And a positive divided by a negative is a negative. You're allowed to include a negative as part of your GCF. It just changes the sign.
Oh, right. Yeah.
Okay. What was the problem with K?
I got the wrong answer. I think I got negative signs wrong. I got 7, but maybe I should have gotten negative 7.
What's the GCF of 7, negative 28, and 49 written in that order? It's going to be 7. So I'm going to factor out a 7, and then I divide 7, I divide 7, I divide 7. 7a divided by 7 is a. Negative 28b divided by 7 is? So it's going to be minus 4b, and then 49c divided by 7 is? Positive 7c.
Oh, I just got the a at the beginning, but I got negative 4b.
Yeah, you see, so we're being a little sloppy. It'll be real deliberate. What's our problem with m?
What's the answer for m? I don't know.
It's going to be 10x bracket 2y minus 1.
Oh, I just got 2y. Okay.
So you guys, I'm willing to bet a bunch of you did this. Again, when you divide, you do not get 0. 0 is never the answer when you divide things. Yeah. For m? No. Why are we pulling out a negative 10x? The leading term is positive, so you wouldn't pull out a negative. Your GCF here is just going to be 10x. So then I divide, because that first term is positive, because the first term is positive, and you want it to stay positive. So then 20 minus 10 is going to be 2. The x's cancel, leaving you with 1, not 0. And then the y is just going to be there by itself. Well, you know, with the 2, but whatever. And then you've got the negative 10x divided by 10x is going to be negative 1. And then n, what's our problem with 10? With n? What's wrong with n?
What was the answer for n?
It's going to be 5xz plus...
I had y as my and then I had y 25.
Sorry, no. It's going to be 5y... Sorry, let's just do this. The GCF here is going to be 5 and a y, and then in brackets it's going to be 5xz plus 12wx minus 7w. That's the answer. What's the question?
I think I just forgot the 5 y.
So you just need to be more careful.
Yeah, but is y 25 x plus 60wx minus 35w still correct?
No,
No?
because you didn't pull out the GCF.
But it would work if you distributed it.
But it's not. You haven't pulled out the greatest common factor. So you can factor it further is the language that we'd use. So Danny asked a really good question that I want you all to hear the answer to. Danny said, well, what if I didn't notice? What if I didn't notice that I could factor out a 5, and I just factored out the y? And I would get y bracket 25xz plus 60wx minus 35w. Is that still correct? And my answer to that is no, because it's not complete. When you're factoring, you want to pull out the largest possible things that you can. Otherwise, the language is you have not factored fully. You have factored partially, which means you're not done.
Is there any time when it'll ask us to just factor partially?
No.
Okay.
The only reason you want to factor is to rip it apart.
Right.
We don't half-ass ripping things apart. We full-ass it.
Yes.
Destroy it. Tear it apart completely. So then T was the last one. What's our issue with T? It's just big. Okay, so let's look at the coefficients first. 30, 12, and 21. Is there anything I can divide out of each of those? Well, 30 is 3 and 10. That's 3 and 4. That's 3 and 7. So I can pull 3 out of each of those. Okay, and so now we look. This is similar to an example I did with you, I think. How many x's are in this one? How many x's are multiplied together in this one? How many x's are multiplied together in this one? So what is the largest number of multiplied x's that I can pull out? 2. Now, same thing with the y's. How many multiplied? 5 there, 4 there, 4 there. So the largest number of y's multiplied together in any one term is 4. It's the common number. Now z's, what is the largest common multiple? Z? 4. So that now is our GCF. So what I'm going to do is I'm going to divide every term by that GCF. If you are struggling with it, I would encourage you to write it out the way that I'm doing this. If you can't carry it in your head, don't be too proud to write it down. You'll get there. We build that muscle up. 30 divided by 3 is? X to the 4th divided by x squared is? Y to the 5 divided by y to the 4? Z to the 6 divided by z to the 4? So that would be one question that we did. That would be a question out of the exponent section.
I just didn't fully factor. I just read it.
Again, classic.
Yeah. I got everything else right.
Let's keep going. Minus 4xz plus 7, just 7. Do not be too proud to write things down. If you can't do it yet in your head, then don't. Write it out. So make sure you get all the pieces. You'll get there, I promise. Okay. Flip the page if you haven't. Are there any other questions? Going once? Twice?
Look at the answer box. I just need the last three and get them.
Danny. There they are. Here we go. Wrong page. Here we go. So, now we have greatest common factored things. What about grosser things? Can I take larger expressions and break them up into things that multiply together to give us those things? Yes. Yes, we can. It's like Bob the Builder, except the opposite. Can we destroy it? Bob the Builder. Yes, we can. Bob the Destroyer. Here we go. We've got a quadratic. One of the things that's going to show up now, you're going to get real sick of these, but this is my first formal introduction to it, and you are going to now see them for the rest of your mathematical career. And it's going to get real tedious, but that's okay. They have all sorts of wildly useful applications in all sorts of areas. The simple quadratic trinomial. Okay, so first of all, a quadratic trinomial. This is this language. You're like, what is quadratic? What does that mean? You might think it means 4 of something. You'd be wrong, because quad means 4, but it's not. So, no. You'd think, but no. Because everything else, often when I introduce you guys vocabulary, we pull it apart and like, this means this. And so this bigger thing must mean this bigger thing. So we look at quadratic and we say, well, quad is 4. You'd be wrong because reasons. A trinomial. What is a trinomial? A trinomial has 3 terms. For something to be quadratic means that it has the polynomial, the entire polynomial, has a degree of 2. What is a degree? That is a good question. What's a degree? The degree of a term is the sum of the exponents on all of the variables, and a degree of a polynomial is the greatest degree of a term in that polynomial. So, a quadratic having a degree of 2 means we've got something that looks like this. And typically the variable we use is x. It doesn't have to be x. And if you remember, we also list things in order of largest degree down onto smallest. Why are we looking backwards? I'm working up here. So degree of 2, 3-termed object, could look something like what? Someone give me a 3-termed polynomial with a degree of 2. That does not have a degree of 2. That is a degree of 1. X squared. That has a degree of 2. Well, but we need 3 terms. We need a trinomial. I'll give you one here, because Danny's given us the first piece. X squared. Let's go to this one. Plus 6x. Yeah, well, but there's, when you're only adding one thing, it's just 2. Yes, they now do. X squared plus 6x plus 8. No, because you only add up the exponents on the variables in a single term. These are in separate terms. We do not combine their exponents. This thing has a degree of 2. It has 3 terms. Let's put this in here. Degree of 2 and 3 terms. And it's simple. What the heck does it mean for things to be simple? No. A simple trinomial is actually defined for us on the next line. A simple trinomial is, so this right here is a generic, this is a generic trinomial. This is the standard form trinomial. We're getting hostile towards the dog. Trinomial. Okay. So that's a standard form trinomial. And the simple trinomial is when this leading coefficient here, a, is 1. When a equals 1, the standard form trinomial becomes a simple trinomial. So this guy right here is an example of a simple trinomial. This guy right here would be an example of a trinomial that is not a simple trinomial. This guy is simple. This guy is general. Okay? So now, I'm just going to, I'll write it out here again. I'll write another one. X squared plus 4x plus 4. So here's a question for you. This is a simple one, yeah. Because the leading coefficient is 1. What do we multiply together to give us one of these simple trinomials? Because now we want to try to factor these things, right? So if we're trying to factor these things, we need to figure out what goes into, what do I multiply together to give me something that looks like this? Have we seen something that looks like this before? Perhaps in this chapter, maybe a couple days ago? You stay where you are, I'll flip back. What did we get when we multiplied something like this together? We got a quadratic trinomial. This one isn't simple because that coefficient's not a 1. But we got something that looks like what we're trying to rip apart today. Let's go back. I'm going to go back another page. Make our life a little easier. Let's look at a simpler one. When I multiply this thing together, what was my answer here? Don't flip back. Just someone rattle it off for me. T squared plus 9t plus 3t plus 27, which that doesn't look trinomial. We got a group, yeah. You tell me, is that simple? Why? It does have a leading coefficient, but the leading coefficient is 1. Okay, so this is simple. So now here's my question for you. If I don't show you this, what we're doing today is we're going from this and we say, okay, I need to generate a method for ripping this thing apart into this. I can't divide everything by it because I can't divide this front term. So which does nothing and is not a waste of time. Look at what we've got here. How did we get this middle coefficient? by adding the number that came at the end of the binomials, right? The constant term from the binomials. Adding those two together gave me the middle coefficient. And how did I get the constant term? I multiplied those two constants in the binomials together. So if I want to go backwards now, what we, not kind of, but no. Don't think about it like that. But you've got the right idea. Here, to get the middle coefficient, we added these two. And to get the constant term, we multiplied these two. So what we have to do now is we have to find a number, or a set of numbers, two numbers in this case, that fulfill that role. I want to find two numbers that multiply to 27 and add to 12. Because that's what we did here. So all of the numbers that multiply to 27 are 1 and 27 and 3 and 9. That's it. Does any combination there add to 12? 3 and 9 add to 12. So then that's what's going to give us these binomials here.
Wait, but how, if we just have the bottom part, how are we supposed to do it?
This, you're going to think about it the exact same way. So now I'm going to flip ahead to the page that you guys are now on, or still on. Let's look at one of these two simple ones that I drew. Let's look at this guy right here through that same lens. I'm going to write it on the side here, x squared plus 6x plus 8. Harwin, it's going to be? How'd you do that, Harwin? So the numbers that multiply into 8 are 4 and 2 and 8 and 1. And does any combination there add to 6? 4 and 2 does. So then we know that our binomial then has to be x plus 4 and x plus 2.
Is there a middle step we could write out before that?
Yes.
Okay.
So here's how I often, here is the technique. And for those of you who like techniques and rules, you're going to like this. Yes, Carolyn? We'll do an example of that. The which? I have not introduced function notation yet. No. You did? You were graphing quadratics in grade 8? Like parabolas and jazz? Yeah, no, that definitely hasn't happened for these guys yet. Oh, German education doing better than Canadian education again. Here we go. So the technique, the way you want to think about this is was I able to sufficiently convince you of the methodology here? You see why it works? I want to go from here to here. I added these two numbers together to give me that coefficient, and I multiplied them to give me the constant term.
But what if there's not, what if it's 2 plus 9? Is that where we switched up?
So to do something like this, again, we just got to recognize what we're looking for. We're looking for a set of binomials that satisfy this. I want the two numbers to multiply to my constant term, and I want them to add to the middle coefficient. Sorry, yeah. So I want them to multiply to the last term, and I want them to add to the middle coefficient. And now this is where, if you can do it in your head, great. If you can't, what you want to then start doing, okay. We good? Okay. You're not helping the situation either there. We want to start listing off the pairs of numbers that multiply to 8. Because that is the thing. Like, everything adds to 6. You give me a number, I can guarantee you I can find you another number that adds to 6. But not everything's going to multiply to 8 nicely. So the pairs are 1 and 8 and 2 and 4. Is there anything else we could look at, perhaps, as that might multiply to positive 8? Negative 2 and negative 4. That could add to, or multiply rather, to 8. Hold on. And negative 1 and negative 8 would multiply to positive 8. So you have to pay attention to the pairs of negatives as well. So then, which set here is going to add to positive 6? This one is. So then my binomials then must be x plus 2, because I want my 2 to be positive, and x plus 4 and x plus 2. What if my polynomial had instead have been this guy? I'm going to do x squared minus 6x plus 8. Now I want my two numbers to multiply to positive 8 and add to negative 6.
And you have negative x minus 4, x minus 2.
Then you'd use this pair, because I want them to still multiply to 8, but now we're adding to negative 6, because again, you have to include the sign out in front of the term. So then this one would instead be x minus 2, x minus 4.
Why not x minus 4, x minus 2?
I could have written it like that too.
Okay. Does that matter?
No, because you can multiply it 2 times 4, well, like, sorry,
Yeah.
6 times 7 is the same as 7 times 6. You can multiply in any order, so it doesn't matter which one comes first. There's no reason for that.
Okay.
It's a reasonable question, but there is no reason for it. What if instead I gave you this one? I'm going to use a different color. Let's go down. I'm going to go x squared minus, plus 2x minus 8. Oh, it's similar, but it's a little tricky. Now I want two numbers that multiply to not 8, negative 8. And I want them to add to positive 2. So now we're going to look at combinations of numbers that multiply to negative 8. What are all of the numbers that multiply, all of the pairs of numbers that multiply to negative 8? Negative 4 and 2. Negative 2 and 4. Negative 1 and 8. Negative 8 and 1. Now, which pair there is going to add to positive 2? It's going to be this guy right here. Negative 2 and 4. Thank you, Aiken. So then I'm going to get something that looks like this. X minus 2 and x plus 4. They're really easy to check. The first thing I taught you guys how to do in this chapter was how to multiply these things together. So to check it, you just recombine it. Do you get what we started with? If you did, congratulations, you ripped it apart appropriately. If you didn't, well, then you didn't.
Is there a way you could accidentally half?
Well, there's all sorts of ways to screw this up.
Okay.
All sorts of ways. Like everything in mathematics, there's often only a couple ways to do it right. There's infinitely many ways to do this horribly, horribly wrong. Yeah, 100%. So, let's put some instructions down here. You just done it. Now let's write it out. What have we done? To factor a simple trinomial, you must find two numbers that, we've established this already, add to the middle coefficient and multiply to the, now this is where things are going to get dicey, because it doesn't just have to be a constant term at the end, it could also be a coefficient. So we're going to say here multiply to the last constant slash coefficient, and I'll show you some examples of where the last one isn't a constant. There's a variable there as well. Are we cool with what we've kind of done here? Okay, so this list here is just what we've done already. We're going to find the two numbers. we're going to recognize that those two numbers then must satisfy a binomial that looks like this, or sorry, two binomials that look like this. We set down our brackets, we multiply, we set down our brackets, fill them up, and we can check by multiplying. So,
Wait, so why is it called quadratic? Is it because there's two binomials?
no one's ever asked me that question, and I've never asked it myself.
Okay.
Let's Google it.
And you have three, and then you end up with four, like two binomials.
Here we go. So, here's the answer to your question. In mathematics, a quadratic is a type of problem that deals with a variable multiplied by itself, an operation known as squaring. This language derives from the area of a square, which I've shown you already back in the exponent section. That's why we call it squaring, because we found the area of the square made of those side lengths. The word quadratic comes from quadratum, the Latin word for square. That is why it is called a quadratic. I learned something new today.
I still don't know why that really. I guess it does.
Because you're squaring, and the Latin word for squaring is quadratum.
Did you never not swear? In one of these?
But that's what. Then it's not a quadratic anymore. Like they're called quadratics because
Because they're squaring.
they're squaring.
The first thing.
Okay, here we go. Nice and easy one. Some of these you're going to get real good at and start rattling off in your head. Number one, what is that quadratic trinomial factored? 10 meet. Good. Done. Love it. Questions, comments, concerns. 10 meet, what'd you do? You want the numbers that multiply to 10, and you want them to add to give you 7. Again, middle term and the end term. And now you just rattled off all those numbers. 1 and 10, 2 and 5. And they could be -2, -5, or -1 and -10. But you said it was those two. The 2 and 5 are positive. So we set up our binomials, x plus 5, x plus 2. Number 2. Oh, sorry, Harman? We'll get to 3. Number 2. Take a look at it. I want you to try it. Try number 2. You've got an answer? Okay, give some of your classmates a sec. I want you all to try it. Do number 2. Okay, so what do we got? Harwin, did you do it? No. No, I'm going to do number 2. I signed number 2. X plus 2. Does anyone want to see how this was done? Okay, so again, it all comes down to the combinations of numbers that are going to multiply and add to what we need them to multiply and add to. What do I want my numbers to multiply to? It's not 14. It's -14. And what do they have to add to? -5. So now, list out, if this is, as these numbers get bigger, there is zero judgment in writing down this combination of numbers here. Are we taking notes? Are we writing down what we're writing down here? Or are we playing with our phone or watches? Okay. I want to, what are the numbers, combinations of numbers that multiply to -14? Negative 7 times 2. Negative 2 times 7. Negative 1 and 14, and I heard also negative 14 and 1. What combination there is going to add to negative 5? That guy right there. It's going to add to negative 5. So my binomials then are going to be x minus 2, sorry, x minus 7 and x plus 2.
Yeah, number 3, I was trying to do number 3.
Number 3. Is number 3 a simple trinomial?
No.
Okay, so let's make a note of that. Let me zoom in on this guy here. I'm just going to put a star here and say not simple. It's not simple, but what do you notice about that trinomial? Look, think. What do you notice? 10 meet. Where? What? What do you mean?
The
10 meet has noticed. There is a GCF of those 3 terms and 10 meet. That GCF is what? It's 2, which happens to be the leading coefficient. So if I pull out the GCF, is it going to leave me with a simple trinomial that we can factor? Yeah. You bet it will. So the GCF is 2. So we're going to factor that first. Oh, there's a reason why I taught you greatest common factoring first, because now we got to use it. We're going to greatest common factor this thing first, leaving us with what? Good. And now I'm going to look at the polynomial piece and factor that back. Well, I took out the greatest common factor, bless you. And now we're going to factor the polynomial, the trinomial in this case. So now, instead of looking at 18 and 40, what do I want my numbers to do? I want them to add to 9 and multiply to 20. Now, if you need to write out those numbers, by all means write out those numbers. But for those of us who are getting a little bit quicker, you're going to notice that the numbers that are going to multiply to 20 and add to 9 are 4 and 5. In this case, when you say 4 and 5, you mean positive 4 and positive 5, yes? Okay. So then the polynomial piece is going to become x plus 5 and x plus 4. And the GCF we had out front must remain out front. Hold on. Are we cool with how 3 ended?
Yeah, but is it also okay to write, so you wrote it as 2 bracket x plus 5 bracket and then bracket and then x plus 4. Would you be able to write it as, like,
The GCF should always be out front.
yes, it would be, but those, you know those,
Square brackets?
square brackets, but square brackets and then those 2 round brackets?
It would be unnecessary.
But that would be correct,
It would not be incorrect.
but it would be less right.
It would be, it's not necessary. So anyone else would be like, why did you do this?
Yeah, but it would be.
It's not wrong,
Okay,
but now you've got questions raised.
okay.
Now people, it's not wrong, but now people are being like, why? What's going on with you? Why? But you're not wrong,
Yeah,
but you're raising eyebrows.
okay.
Okay, number 4. Carolyn, you wanted to jump in on 4. Similar idea. This is not simple because the coefficient is not 1. It is. So Carolyn, take us away. Oh, you want to rewrite this as 2x plus 10 and x plus 4? If the instructions say factor fully, this is still not fully factored. It's not wrong, but it's not fully factored because you can still pull. It's like with a prime factorization. You want to reduce it down as far as you can into all of the fundamental bits that make it. So because I can still pull it, it's not wrong. It does multiply back to give me this, but this is not factored fully. This is.
Okay. And you just distribute that 2 onto the first bracket?
Yeah.
Okay.
and then, well, how I would, if I were checking my work here, I would multiply the binomials together first and then distribute the 2 in.
Oh, I see. Okay.
But yeah, either way would work. Okay, so Carolyn's pulled out the negative, leaving us with a squared plus 11a plus 18. Now what are we going to do? Factors for negative 8. I want to multiply to negative 18, and I want to add to. Sorry, I lied. Ugh, I'm looking at the wrong part. It's 11. So you said 2 and 9. 18 and 1. 6 and 3, I think, is the other one. The one here that's going to add to 11 is. So then I'm going to get. Finish this off, Carolyn. Cool. And the GCF, that negative 1, stays out front. We see the technique? Comments, questions, concerns? The only way you're going to get better at these things is to do a metric ton, like a literal metric ton of practice. So I'm going to give you a literal metric ton of practice. Before we do that, I want to do one more example with you. What if I gave you something that looks like this, and then Daniel answer the question? I know. Number 5, here we go. I want to do the following question. X squared plus, I'm going to go back here and I'm going to use one of these combinations of things. Plus 7xy minus 8y squared. This is different.
Wait, but I have a question.
Yeah.
So I get how we got that answer with the number part, but then the a, we have two, like a times a plus 11a plus 18, and then we end up with just, like, I get once you distribute it. No, I don't. No, because negative, then you just get negative.
No, but you're going back to here, Danny.
Yes. No, but.
So 9 times 2 is 18.
No, here, the next one, if you distribute that negative, you just get negative a plus 9.
You distribute after you've combined these, so you get negative a squared minus 11a minus 18.
I get how the, okay, so that would be better to distribute that, and then distribute the negative.
Well, you're multiplying a negative 1 on everything, yeah.
Yeah. Okay.
My new question, number 5. How is this beast different than the previous beast?
That's another square thing, and more variables.
Sorry? There's another variable in there. Is this thing still simple?
Yeah.
Yes, because the leading coefficient is 1. Is it still a quadratic? Quadratic required a degree of 2. What's the degree? 2. It's still. Is it a trinomial? You bet it is. So this kind of question is still valid. What are you going to... If the y wasn't there, what would our answer be? 10 meet. I see that hand first.
X minus 1 times x plus 8.
Correct. If the y isn't there, then it would be x minus 1 and x plus 8. Because the numbers that multiply to negative 8 are going to be negative 1 and 8, 1 and negative 8, yada, yada, yada. But you want them to add to 7, positive 7. So the numbers that are going to add to positive 7 are going to be negative 1 and positive 8. If we think about how these things were distributed, x times x gave me my x squared. The x times the 8 give me the x in the middle here. This negative 1 times x gives me the x for the middle here. And then the negative 1 times 8 would just give me the 8. What does this y squared here and this y here do to these two binomials? Think about what you'd have to do to get that y squared here on that negative 8. I'd have to have a y times y somewhere. Oh, it makes perfect sense.
No, but I was just guessing.
Because the negative 1 times that positive 8 is what's going to give you that negative 8. So if I want it to be not negative 8, but now I want negative 8y squared, it's not just going to be negative 1 and 8 now, it's going to be negative 1y and 8y. And then what does that do to the middle term? Well, I'm going to have x times 8y. That's going to be 8xy. And then I'm going to have negative 1y times x, which is going to be negative xy. So I'm going to have 8xy and negative 1xy giving me our 7xy. Do you follow what happened here? Does it make you uncomfortable? But do we cut? Sorry, Angel? Which part? The part where I explained it at the end? Okay, so the placement of the y's comes back to when I redistribute these things together, when I multiply the binomials back together, what do I have to do to get that y squared here? If I multiply the x and the x together, I'm going to get x squared. When I multiply these last two terms together, I'm going to, yes, for a reason. Trust me, Danny. To get this last term here, I multiply the last term in each binomial together. If the y is not there, it's just negative 1 times 8 gives me negative 8. We're good.
Right.
But I don't want negative 8. I want negative 8y squared. So to get a y squared here, I have to have a y times a y. So I have to have a y that shows up at the back of each bracket. So when I multiply these two things together, I'm going to get negative 1y times positive 8y, giving me negative 8y squared. And then the question is, what's going on in the middle here? Well, to get the middle two terms, I'm going to do, I did my first, I did my last. Now, my outside ones and my inside ones need to get multiplied together. The outside one's going to be x times 8y. Well, that's just going to be plus 8xy. And then I'm going to get minus y times x. Well, that's just going to be negative xy. What is 8xy minus xy? Angel, does that help at all? Okay. This is where you guys now have to do a crap ton of practice to get good. I am done doing questions with you. Got to kick the birdies out of the nest at some point. And you will either fly or you're going to smack into the ground real hard and die. But I hope you all fly. Here we go. So, your homework is as follows. You're definitely doing all of the next page. This next page here. You're doing all of this page here. Remember now, you're not just factoring trinomials, you're also, or you're not just using this new technique, you've also got to see what happens when I've got something looks like this bad boy. What are you looking for here? A GCF. You're looking for a GCF. Is it obvious that, why? Because I want to make these things simple. Because it's not simple. We've got to make it simple. Make it simple.
Okay.
So, is it obvious to you that 3 goes into 84? No. But now you got to go check, see if it does. So, divide and see what happens. I want you to do all of those. Do I want you to do some of these? Yeah, we're going to do some of these. Oh, is it possible that you're going to come up with some that don't factor nicely? Yeah. They're not undefined. What I want you to write is, if you come up with one that isn't factorable yet, I want you to write down the words, not yet factorable. Because it's going to become factorable later. I just haven't taught you how to use those tools that are required for making it factorable later. Sorry? It means it's not you can't find the numbers that multiply to the last and add to the middle. But I'm going to teach you how to do it later. You will eventually. So if you can't do it now, you will eventually have tools to do it. Carolyn. Number 3 on the other side. What's your question? Yeah? Just play with it. It's doable. I tell you, that one is factorable. 100%. I just did it in my head. It's totally doable. Okay, so I want you to do all of those. I want you to do a bunch of these. I want you to do, which ones do I want you to do here? I want you to do the odds on this section here. Odds. And there's 2 pages to this. This one and this one. You're doing odds on both sides of that. Do I want you to do more? Well, you're going to do more later, but we'll hold off on that. Oh, you know what? No. Yeah. No, I want you to do this page too. Not all of it. I want you to do aces, which is this stack here. Aces. The first page is all, then odds, then aces. ACE, and then you keep alternating letters. It's like the odd letters, but that doesn't make sense because letters can't be even or odd.
Yeah, but okay, that's I just gonna ask that.
Yes. Aces is the odd letters. There aren't. That's why I said aces. No, it's even. Can you go up at one? Soon. I started. Today, Wednesday?
I think we should do it very long ball.
What are we doing?